All right, everyone, let's get started here. If you're online, make sure that you turn on your cameras. Okay, so last class we finished talking about soil EC lecture. We went through that, how we can measure it, what types of properties affect the reading that we get, and how can we use that for precision ag, especially trying to relate that to texture and its connection with yield, and how we can use that information to better understand what's driving yield across a field. So today we're gonna start on the exercise that actually implements some of the things that we learned in the lecture, but now with this data set, it's a soil EC data set that was collected using Navaris. And just a quick reminder, we do have our midterm on Wednesday. It is going to be in person. So it's not going to be able to be completed via Zoom. You're going to have to come to your respective campuses. So in Athens, this room here is going to be where we're going to meet on Wednesday. In Tifton, it's going to be the same room as you all have been meeting in person. And the same thing for Griffin as well. So it will be in person. You're not going to have to use a computer. It's going to be on paper. Bring a pen to use. And I'm going to be asking you, as we already talked about, some questions related to what we've been doing, some of the main functions we've been using, like how do we do X in R? How do we import a data set? How do we do things that, again, the goal is not to be tricky, it's just to see if we're really understanding what we're doing as we're doing things. And well, I guess that was it as far as the midterm or comments about it. And the way that I have today's class designed is we're not going to do a comprehensive review of like getting ready for the midterm, but today's class, I want it to be a lot more interactive. So I'll be asking a lot more questions to all of you, everyone that's attending live. And we're going to build this script together. So parts of it, I'm going to give already to you, as you know, but then I'm going to be asking you what we do next. What do we do next? So this script and data I have shared with you probably, I don't know, it's been a few class periods ago that I thought we were going to get started on this earlier. So we already have this. It was an email that I sent you where I told you that I had the GitHub files or the files uploaded to GitHub, and I asked you to download the data and the code and to go ahead and create the code data output folders, create the project, all of that inside of the folder called 06 Soil EC. So I'm assuming you already have done this because I have already asked you to do it. If you have not, you're going to have to catch up. But if you have followed the instructions, you should have this ready to go. So go ahead and launch your rproj. Again, we always launch, it's better to launch the rproj instead of double clicking on a script file. So let's do that and launch this project. You probably, so again, we know it's the right project because we have the project name up there. And we come here on the bottom right tab, bottom right window, click on the Files tab, click on that blue button to take us to the home folder of this project. Click on code and then click on the partial. So we see. Yes, somebody has a question?
It's me. I can't see your screen.
Who is that?
Omar.
Omar. Okay. Can other people online see my screen? Okay, see Matt nodding yes.
Yes, we can.
Yeah. Okay. So we can. Okay, so maybe it's something on your side, Omar, because I think others can see.
All right. Yeah, now I can see your R console, R environment.
Yeah, that's the screen that we're working at. Yeah, so we should be good.
All right.
Okay, so if you launch the 0303 Soil ECA partial script. This is what it should be seen. So today, the objectives for this exercise is for us to import soil apparent electrical connectivity data. Then we're going to interpolate that because it is a point data. We're going to interpolate that to have a continuous raster layer for that for 2 different depths and soil depths. These are, if you recall, the various gives you information at 2 different depths. So that's why we're going to do interpolation for both. And then we're going to export this to file so we can use later. We can come to the next chunk. I left you all the packages we're using already. You know, I guess at this point, we probably have been using these packages and talking about them a lot. So you probably know what functions we need from them. But, you know, this is also something, you know, I mean, you don't have to know everything about every package, but at least if you have some idea of which packages we use for data wrangling, which ones we use for, you know, SF plotting and so on, it's also a good thing to know for the midterm. So just go ahead and click play on that package on the chunk to load all the packages. By this point, you already know if you don't have one of the packages, you know how to get installed. So, but we should have all of them by this point. Someone has a question? Okay, maybe not. And I also left you here, we're just defining the theme of the map so we can use consistently for different chunks or different plots. So I left you all the code already. You can go ahead and hit play. Okay, so first thing that we're going to do, as always, is bring in the data, right? So how do I know what function should I use to bring in a data? You know, the first thing is to look at how that data is stored on your computer. So I just want to come here on the data folder, and I have the soilec.csv. So let me see. Let me start here. Bo, what function should we use here to bring in this data set? Not yet, right? So this is a CSV file, so it's not a GeoJSON or shapefile. So what function we? Right, that's it. Thanks. Yeah, so we use the read_CSV. Open and close quotation marks, go have your cursor between there, or / to get outside of the.
Hey, Dr. Bastos.
Yes.
Really quick, it might be a really simple question, but why is it that sometimes we use read.csv and other times we do read_CSV?
Yeah, so I've been trying to use read_CSV for the most, I mean, every time that we're reading CSV. So the read.csv is a function from base R, which we can also use. It's not, you know, it's going to be the same results for the most part. I do prefer the read_CSV because it treats it as a tibble, and we don't have to get into that conversation now. But I mean, yeah, I guess you can use either one to import a CSV.
Okay.
I do prefer.
I just need that clarification.
Yeah.
Thank you.
Yeah, no worries. All right, so // we go inside of the data folder. We just hit tab and it should already autocomplete for you. So let's bring in that. We have some messages here, but nothing. I mean, nothing too crazy. And we do see the ECA object on our environment. If I go ahead and print it, this is what we get. So we have about 8,000 rows for this data set in 7 columns. This is how the columns are named as of now. So FID, F1, F2, F3, 4, 5, and ID column. Not very useful, right? I mean, if you get this data set from a producer or maybe someone you're working with, maybe you can make some guesses to what these columns are. The best thing is really to get them named already, but that was not our case. This is how the data got to me. So I'm going to be telling you what these columns are in a second here, but this is just so you know, real data in real life comes messy sometimes. And this is not hugely messy, but it's some of the things that we have to keep in mind when we're working with data. Okay, so I I guess one thing that we could do quickly here is just, I guess I don't have my code here, but we can just do a summary, right? So always good to check. Let's do a summary of ECA. So we check the values, if we have any ANAs, and how that's all being interpreted by R. So it seems like FID and ID are just like the number of the cell, perhaps, which is, we don't really need that. And then F1, at least with how many decimal or how many numbers after the point we're getting back from R, it's all pretty similar, but it's probably not, because as we print the data, we have more numbers after the point for those columns. It's just how R is printing for us. They're all numerical, right? Because we do get a statistical summary. We are not getting, so if we get a statistical summary, it's because it's interpreted as numerical by R. Yeah, so no NAs. So, and values, of course, we don't know what they are yet, but I guess they kind of make sense once we know what they are. Okay, so first or next step in every analysis is to do some wrangling, right? So I want you to notice these patterns, right? So we bring data, we do a quick exploration of that, we do wrangling, perhaps we explore again just to make sure our wrangling did what we wanted or we thought it would do. And then we do some analysis and then export something out of it, either a data set or maybe a plot or maybe a table. Okay, so we're going to do some wrangling now, right? So let's start here with the object that we have, ECA. Let's add a pipe. And, I guess it's a good practice, even though here is not hugely important, but I think it's good practice to just go ahead and do a clean names, just so we have our names standardized lowercase, the column names. And so I do have here, okay, so I want to tell you what I want to do, and I want to see who can help me here to figure out how to do that. So I want to basically select some of the columns that have the actual data. So for example, I don't really care about selecting FID or ID. I want to select the ones from F1 through F5, but I also want to rename them on the fly, because I will tell you what these columns are, even though you would not know necessarily if you didn't have this information beforehand. So what is the one function I can use here to both select columns and rename them on the fly?
Select function.
Yes. So let's go ahead, add a pipe, do a select function. So this F1 here is basically the X coordinate in WGS coordinates, so in degrees. So we're going to say X. I want to rename it to X and say X equals F1, right? So, one thing to notice is if you think the other way around, if you tell first the column you have and then the name you want to rename it, it's not going to work. So if I do F1 equals X, it's not going to work. You first have to give, if you're doing the renaming on the fly, you have to first give the name of the new column and then what that is in the current data set. So X equals F1, at comma, F2, Y equals F2. So F1 and F2 are the coordinates in this data set, X and Y respectively. So F3 is electroconductivity at the 0.30 centimeters depth in decisiemens per meter. So the way I want to say all that in one name is to call it ECA 30 underscore DSM. So again, I'm saying that it is ECA, the depth, and then the unit in decisiemens per meter. I want to say ECA 30 underscore DSM equals to F3. That's what the F3 column is. The F4 column is well, let me just take one quick step back here and say, remember that various gives you, most various units gives you electroconductivity, apparent electroconductivity at two depths. So the first depth is normally called just a shallow EC, and the second depth is called a deep, or yeah, I guess deep EC is probably what you're going to see. So that the shallow one is the one that in this case is F3 in this data set, and the deep one is the F4. So for the deep one, I want to say ECA 90 underscore DSM. Again, I'm just giving it the depth. So 90 is the depth, and then DSM is the unit of the electroconductivity measurement. And this is going to be equal to F4. And then finally, something that's interesting is that a whole bunch of precision ag equipment, including various, gives you elevation data as well. For this data set here, elevation is on the column F5 and it is in feet. So I just want to call that 11_FT for feet and just say equals to F5. If you have your commas right, if you have your pipes right, your parentheses right, and you run it, this is what we end up with. So we basically selected the columns that we just specified up there, and at the same time, we renamed them to something that makes more sense to us. Okay, so my next thing here is, this is a tibble, which you can think of as a data frame. It's not an SF object, it's not a vector object, it's not a geospatial object yet. Tyner, how do we transform this to an SF object? What function should we use? No. So mutate is like if we're creating a new column inside of the data set, we would use mutate. But to transform this, which is just a data frame, into an SF object. No, okay. Emma, what do you think?
I would have said transform as well.
Okay, so transform, we use ST transform, and we're actually going to use that here next, but that's not the function that we need here. Trip, what do you think?
I was thinking mutate transform as well.
Okay. David, what do you think?
Yeah, I was thinking the same.
Okay,
ST as SF.
yeah, so somebody online said, who was that?
Peter.
Peter, awesome. Yes, Peter, yeah, that's right. So we use ST_S_SF. We've been using this function a lot. Make sure you know this for the midterm, because you're gonna need to. So if we just say this, we have to tell it which columns have the spatial information, right? So we do that by using an argument called chords. So we say chords equals to, and then we give the names of the columns that have the X and Y values, which in our case, we already renamed them to X and Y. Just have to use the C function and then specify X and Y using the quotation. So we just say that chords equals X and Y. So if we run this and now we print it, as we know, we remember now that SF objects here when we print them, they give us two panels, right? So one is just telling us it is a simple feature collection with X number of rows. It is a point vector file, gives us a bounding box, and also gives us information about the coordinate reference system, which right here is NA, because CSV files do not contain information of coordinate reference systems in themselves. And then if we come on the second panel that it prints is basically the same data as we had before, except that now the X and Y columns are not here because they've been recoded to a geometry column that now has a point for each one of the rows in this data set. Okay, so is it ready, or do we have to do something else with it? We have to assign a CRS, right? How do we do that, Arminder? Which function?
Give me a sign.
I don't think that is a function. Well, so let's first think of the function that you would use for that.
No.
So we're getting there, but not quite yet. So Dennis said ST transform. ST transform is when you already have an assigned CRS and you want to transform that into a different one. In this case here, if you look, we don't have an assigned CRS. We still have to assign first and then transform, right? So how do we assign a CRS to something that doesn't have a CRS yet?
ST set CRS.
Yes, who was that?
It's Secker.
Awesome, thanks, Checker. So yeah, that's right. So we use a function called st_set_CRS, right? So we're setting the CRS first. It has an argument called value where we give the EPSG of what was the native CRS of this layer when it was collected. So remember, it's not what you want it to be, is what it actually was when it was collected. In this case, it was WGS 84. So we use the EPSG for that, which if you don't remember, and perhaps you should for the midterm, is 4326. Okay, so if we run that and we printed, we see that now, before it was saying CRS equals NA, now it says geodetic CRS WGS 84. Sandesh, are we ready, or do we need another step here in this rendering? We have to transform, is that what you're saying? And why is that? Why do you think we have to transform? To get to what? Sorry, say that again. Yes, in the meter system, yes. And why do we need this to be in the meter system? Dennis, can you help Sandesh here? Why do we need this layer to be in a meter system? So in a UTM instead of WGS, which is degrees. Say that again. Okay, to make projection, I guess that's not wrong, but it's not what I'm looking for.
It's more accurate and when we sign anything change in meters or raster size, shape file and all the things are in meters. So if we make a grid, it will be in meters to make it is later on easier.
Okay, yeah, that's, so Amrinder was saying, because if we use a grid, we need to be in meters because of the unit of the grid is going to be meters. That's a good answer. Also remember that we're going to be interpolating using a grid, because we're going to do interpolation is a distance-based function that we need for our layer to be meters. So yes, that was the same line of thought, I guess. So we just go ahead and add a pipe. So now how do we transform this from WGS 84 degrees to UTM in meters? Let me see somebody online. Anish, what do you think? What function should we use here to transform from WGS 84 to UTM?
Yeah, EST underscore transform value is equal to.
Yes, that's exactly it. Thanks, Anish. So notice now ST transform is when you already have assigned a CRS and now you want to change it to something else. So we use ST transform. It has this argument called CRS. And now here we give the EPSG of UTM, NAD83, or NAD, yeah, I don't know what to say here, maybe NAD83, zone 16 north, right? So this is the EPSG for that is 6345. So now if we run this and now we print it, we come on the first panel here. Now it's saying that it is projected on NAD83 UTM zone 16 north. That's what we needed. And and again, I just want to make the point that everything we're doing today in this exercise, we have done at least 3 times. So all these functions here we've been using a lot. Make sure you know what they're doing, each one of them for the midterm, because you're going to be asked about that. Okay, so I do want to do a quick plot here. As always, it's good to plot your data and see how it looks like. So we're going to start off with the object that we just created above, which at this point is an SF object. So we're going to add a pipe here. Start with a ggplot call, add a plus. Remember that once you start ggplot, you use pluses instead of pipes. So what function or what geom should I use to plot this this object here, right? So if I just print that object, it is a simple feature object. What geom should I use here? Yes, GeoMSF. I've heard a lot of people saying that. That's great. And I do, I want to tell you what I want to visualize, and then maybe you can think easier about how should we specify that in coding. So what I want to see here is a map of this field. GeoMSF does that for us because a map needs geographic coordinates. GeoMSF is working that side of us, or that side of it for us. But I do want to color my points according to EC at 30 centimeter depth. How do I do that here? What's the next step to make that happen here? Let me look for someone online. Let's see, Tifton. Can someone, maybe Miller, what do you think? How do we color the points according to ECA 30?
Don't we have to put like the theme varieties and then add in your colors like you have in that first chunk, kind of like your theme?
So it's not on theme. It's here within GeoMSF. Omar, what do you think? What do we need here?
I think we need fill is equal to that column name.
Okay, let's try that. So if we do fill equals, if we do this, let's try that. Okay, it did not work because it's looking for an object called ECA 30.
AES function, aesthetics,
Yes, who said that?
Anis.
Anish, perfect. Thanks, Anish. Yes, so remember, if we're changing something in the plot that is changing according to a column, it has to go inside of AES. Right, so make sure you have your parentheses, closing parentheses matched up, and if you run it, that's almost what we get. So what's happening here is that the points should actually be, we should actually change the color instead of the fill. So, but we were almost there. So if we just change, instead of saying fill, if we say color, we do get what we are looking for. Awesome. I do want to change the size of the points. So I want to add a comma. I want to change that. So if you get out, so now notice that we're changing size to a fixed value applied to all the data points. So that has to be outside of the AES function. We say size equals, I want to change to 0.5. So we really see now the passes of the various, right? So decreasing the size of the point allows us to see the passes of this implement. And I also want to change the color scale. I want to use these. So add a plus. We're going to change to scale underscore color underscore varieties B for bin. We run that. This is what we see. And lastly, I want to add our theme that we created on the second chunk. So just add a plus, and the theme was called my theme underscore map. So this is how it looks like. Okay. If we come on the, so this is for the 0-30 centimeter depth. Remember, we also have so this is the shallow depth. We also have a deep depth. And we can just basically, you can just go ahead and simply copy this code here and paste on the chunk below. If we just even delete that ECAW that's there right now, just paste the whole thing there. We do have to make one change though, and make this show the data that we want, which is the deeper depth, right? What is that change? Yes, yes. Thanks, Tanya. So yeah, that's right. We just changed the ECA 30 to ECA 90. If you remember, our data set coming in has those two columns. We're just assigning the second column now to that color. Okay, so we do see there is some variability here of ECA, both shallow. So this is the shallow one, and this is the deep one. We see there is some variability. If you notice the shallow one, the values range from, let's say, 0 to, so 9 is not the maximum here. To get a better idea of the range, we should actually go back. But just looking at the legends, right, and working with what we have here in front of us. So this is ranging, let's say, from 0 to probably 10 or so. And the deeper one is ranging from, let's say, 0 to probably about 13, give or take. What does that mean? So what does it mean if I had if you were to tell this farmer, your shallow soil layer has more X, and X could be sand or clay than your deeper soil depth. So if we think of, so the shallow has lower values than the deeper. What does that mean if we're trying to relate this to texture, I guess is the question I'm trying to ask. What would you tell this producer? Which of the depths is coarser in texture? Okay, we have a whole bunch of people saying, but let's, I saw Tyner is starting, so go ahead, Tyner.
Deeper soil probably got more like clay, and it's got higher EC, as well the top soil probably got more sand.
Okay, so for those online, Tyner said that the deeper soil here probably has more clay and the top layer probably has more sand. Does anyone disagree with that? I'm glad no one did, because that's exactly what I was going for as well. Yeah, so lower EC, it means you have, I mean, of course, remember, a whole bunch of things can control soil apparent EC. In this case here, we're making the assumption that is being controlled by texture. In that case, a coarser texture has fewer sites to react with soil ions, or cations especially. And so that we relate that to conducting less electricity through this measurement. So a coarser texture would have lower soil EC than a finer texture. So a more clayey soil would have higher EC. So that's exactly what I would also think of this. Okay, so we brought in the data, we wrangled it, we plotted to explore the initial data. Now, as you know, we are going to interpolate both of these layers to have a continuously even layer that we can export. Whenever you hear interpolation, regardless of which type of interpolation it is, you should be thinking of a grid. To do a grid, we do need a boundary, right? So let's bring in the boundary of this field so we can do the interpolation. Let me see here. Ethan, so we already have, I want to tell this, if you don't remember, I mean, for all of you, we already exported the boundary as a GeoJSON. That is in the file system in a different folder. We're going to navigate to that folder. So it is a GeoJSON already. What function do we need to use to read a GeoJSON object or file into R? And that question,
read us.
yes, read SF. Thanks, Ethan. So let's go ahead and do the assignment. We do read _ SF. As we already talked about this, we could have copied that boundary.geojson and pasted inside of our data folder of this project. I did not ask you to do that because I think that's not the best way of going about it. We're actually going to navigate to where that original layer is. So if you open and close your quotation marks, and if you have been following the same naming scheme as I have in class, which you didn't have to, but if you were, then your path should match mine. So I want to do .. to get outside the code folder. I hit tab. I am inside of my 06 OEC project. I want to get outside of that because I want to get into another folder's project. So .. again, that brings me to my main course folder where I see all my folder projects. That specific file is under the 04 EO Monitor project. So I go on that project. I hit tab. I go inside of the data folder. That's where we exported that layer. And I hit tab again, and I want to bring in the boundary.geojson. So that's the boundary that has already been wrangled, and it's already in UTM, or I think it's already in UTM. No, it's still WGS84, but it's at least already a geospatial file. Again, if you we're not, if your path doesn't match mine exactly, I hope you can still understand what we did and how we got where we got. If you have issues, let me know. But that's what we wanted to do. So if we just run this and then just print the boundary W, we see it's already an ASAP object. It is a multi-polygon. Somebody had a question? No. Umar, I think I'm gonna mute you because I think I'm hearing some echo, but I'm gonna do that. But if you need to ask something, feel free to unmute yourself. Okay, so we brought that in. If we just print it again, it is WGS 84. As we just talked about, we have to have that in meters. So let's change this again as we did previously. And now I just want to ask another time, maybe David. Now, can you recall which function we should use here to transform from WGS 84 to UTM? Yes, ST transform. So let's give a pipe, use ST_transform. It has this argument called CRS. We give it the EPSG of UTM zone 16 north, which is 6345. Just run that and we print it. Now we see on the first panel, we have NAD, we have what we were after, right? So again, I think it's always good for us to do, or actually, no, never mind. Let me take a step back here. So we brought in the boundary. Now let's create the grid, right? So if you remember, and this could easily be a question Wednesday. We're gonna first create the grid as a vector, and then we're going to transform that grid to raster. And the reason for that is because the function that we use to interpolate only accepts grids as raster. If we give it a vector grid, it's not gonna work. But that's why we do that step. So let's come on this next object here that I want to save the grid. We're going to start off with the boundary, right? Because that's the cookie cutter we're using to determine the grid, the extent of the grid. We're going to give it a pipe, and the function that we use to make a grid is actually pretty intuitive because it's just st_make_grid. So notice boundary is SF, it is vector. We're using a function that's going to make a vector grid. The one argument we have to change is called cell size. We say equals 10. And here is where it makes a difference if this, if the incoming data is WGS 84 in degrees or UTM in meters. So this unit depends on the CRS that your data is coming in. If our data, our boundary is already UTM, then this is 10 meters. If it were WGS 84, this would have been 10 degrees, which makes really no sense. So again, why do we transform this from geographic, or in other words, in degrees, to projected, or in other words, metric system? So if we just, if we just do that, and then we just printed, we see we have like 6,000 and some cells of this. Is still an SF, it's still a geometry. We have to transform this back, so right now, as you can see, we're not seeing that data set. We have to make it look like an SF object. This is kind of confusing, so I don't want to confuse you. Let's just go ahead and do st_s_sf. Just when we apply the st_make_grid function, it changes slightly. The way the R sees this object is still SF, but it's not a full SF with like the data set that we see. So that's what we're doing this next step here. But don't worry, that's just a detail here that you're not going to be worrying too much about. You getting there? So go ahead and print your boundary W, make sure that it is in WGS, or I'm sorry, make sure that it is not in WGS, make sure it is in UTM. And if it's not an UTM, then you're probably gonna have to go back to the chunk above where we did that transformation. So while Dennis is looking over the code, every time you run into code issues, the first thing I would look for is if you have the pipes in the right places, if you have the closing parentheses the right places, if you have commas in the right places and so on. Those are the most common coding issues that I would always try to identify first. And then if it's really something that the function is, if you check all those boxes, then maybe you're gonna have to do some Googling as well. But those are always the first things I would look for. Did that work, Dennis? Let me come around and see. Can I check? I'm not sure what happened, but now it's working. I think it's probably maybe a spelling error. Okay, so now the next thing is we need to make this grid, which right now it's in a vector format. We need to transform this to raster. And that in itself, there are a couple ways of doing that. For this specific case, the way we're going to do it is using a function. So add a pipe there, hit return. We're going to use a function called st_rasterize. And this function here basically is transforming something from vector to raster. And we need to give it the dimensions of the raster cells. So it doesn't simply learn from the one above. We have to give it again here. And the argument for that is called dx, for distance on the x-axis. We say dx equals 10 and dy equals 10. This is how we do that. So if we run that and we print it, it is now a stars object, and it became a stars object right here, this st_rasterize function. And then lastly, I just want to crop this raster to the boundary of the field, so we don't interpolate outside of the field, right? We already talked about this. It makes no sense to interpolate outside of the field. So let's add a pipe, and we use a function called st_crop. Oops, crop. And we just give it the shape that we want to crop, or use to crop the raster. In this case, we want to use the boundary, right? So the boundary is our cookie cutter that we want to cut that or crop that raster using that shape. So if we just run that and we print it, we see again, it is a stars object. Remember, the way that stars objects appear is slightly different from an SF objects. So here just gives us the column names, in this case is ID, and just gives us a summary of that column. And we have a whole bunch of NAs. I left you the code for plotting what we just created so we can actually see it. We have seen this many times already, so we should not be surprised by anything here. But one thing is that the ID here is basically just a cell number, which is not very informative at this point. This is just a grid. And it's already coloring by ID, which again is not very useful. But then we have all of these gray cells outside here. And that's because, well, the cropping, right? So we cropped this layer to the boundary. So everything that was outside the boundary was assigned an A. Remember, rasters, the cell is still there. It's just that now that all of those cells are coded as an A instead of having an ID value. Okay, so let's go ahead and interpolate this layer here.
Hey, Dr. Bastos,
Yes.
really quick, when we did that GT plot just then, mine doesn't look like yours. It's just like a blue square.
You mind going up just a wee bit?
So maybe make sure you have this pipe here connecting with the ST crop, because maybe if yours stopped right there, then I think it would be just all blue.
Yeah, without the boundaries.
Yeah, so if we let's try that. So if I just comment off here on this pipe and I run, so it stops here, it doesn't crop. If I plot it that way, it's just a square, because it's basically taking the bounding box of the boundary and just having a continuous raster that has numbers in all cells. But then when we crop, that's where we basically see that shape of the field. Because again, now every cell outside of the grid, or I'm sorry, every cell outside of the boundary is being assigned an A because of that ST crop using the boundary.
Yeah, I have the pipe in and it's still just giving me the square.
I had to run my, like that first part of the chunk separately from the
Yeah,
grid R now.
yeah, I'm running mine separate too, but it's still.
And then I could run the whole chunk.
Okay, that's kind of odd. Well,
Well, mine like,
Oh, okay, I got it. Never mind. I don't know what I did different, but it works now.
okay.
Sorry.
No worries. Was everyone else able to visualize this? And this is, you know,
Yeah,
again,
I'm
I think it's another important point of why it's always good to do something and then visualize what you did. Because if you just stop here, you know, and let's say if for some reason it was not cropping and you just stopped here and you just kept going, assuming that it had been cropped, you would not have caught that issue. So it's always good to plot, make sure that it's doing what you think it is doing. Okay, so interpolation, right? So we have our grid now. It is a raster grid, and again, it is raster because that's what is needed by the function that we're going to use next, which is the function to interpolate. So if you recall, and this may very easily be a question on the midterm, is how do we do interpolation? Which functions we use, and why, and how does that process work, right? Because for most things here in R, we basically use one function to do something. In this case here for interpolation, we actually have to use two functions combined together to get the actual interpolated map. So the first thing here, I left you the name of the object already. We're just going to use the assign symbol. And if you recall, interpolation again is happens in two different functions. So the first one is where you set what is being interpolated, and the second function is where you basically predict that using the first step and also the grid in raster. So can anyone help me here of which function we set what is being interpolated first? What is that function called? Gstat. Yeah, so Sundar said Gstat, that's exactly right. So we use a function called Gstat from the Terra package, I guess, or Gstat package, actually, yeah. So it has this first argument here that is formula. This is where we define which column we're interpolating. I just want to print, sorry, I'm just going above here just to get that object name again. So, well, ECAW, that was easy. So I just want to print here so you see again the column names, right? So what I do want to interpolate first is the shallow EC depth. So that's the ECA 30_DSM. So the way that we do this is we just say that column name and then we give it a tilde1. It's just, you know, the way that this formula works. I believe it's because there are different ways, different interpolation methods that we can use here, where we would use tilde and then another column name. We're not doing that. We have not learned that in this class. I'm not expecting you to know that, but that's why we have to do tilde1. And then really the next step is just to say data equals the data frame that we're using, which is ECAW. Right, so if we just run this and we print it, it is just this weird object that is just saying formula equals this and then data dimensions. So interpolation has not happened yet. So I want to finish this next chunk here, so we at least finish the interpolation step, and then I'm gonna give attendance or open attendance on GitHub. So if you can hold on for another 3 minutes, please do so. If you have to leave, you can leave, and then you can just send me an email later saying that you were in class. I hope that's gonna be an exception. Okay, so to do the interpolation now, we give it the assigned symbol, and then we use a function called predict. Again, this can also very easily be a question on the midterm. How do you do interpolation? Which functions do we use and what sequence they need to happen? So in this predict function here, we just give it the object we created above. So we see IDW mod, so you can just copy that and paste if you wish. And then we also give it the grid that we're interpolating over, which we also just created above, called grid _R for raster. So if you run that, it's gonna quickly do the interpolation for you, and we can just print it. This is a stars object. It has a whole bunch, or it has 2 columns, right? So var1 pred and var1 var. We talked about this, of why we have these 2 columns and why var1 var is all NAs. If you don't recall, you know, it's also something good to remember. But the one that we're really interested in is var1 pred. And I'm going to stop here with this exercise. I don't want to keep you all for too long. I just went ahead and saved my script, and I want to launch my GitHub here so I can open the issue for attendance. Attendance March 13th. Please go ahead and claim your attendance if you're attending live. And yeah, I guess today, you know, all the questions I've been asking you today are things that can easily be in the exam. Again, we've been doing this for many times at this point. If you were, you know, if you didn't really know the answers from the top of your head when I asked you today in class, use that to your benefit and identify what you need to study for the exam. That's probably a good pointer as well. If anyone has any questions or issues, let me know. And so again, on Wednesday, you're gonna have the midterm, you're gonna have the full 2 hours. I don't think you're gonna need all that, but if you do, you will have 2 hours to complete it. And you're not gonna need a computer, although I will be asking you questions that some of them are gonna be code related, just like as I was asking today in class.
So, for the students like here in Tifton and off campus, are you gonna like send one of us the test for us to print out, or
Yeah, so
like how exactly is that gonna go?
Yeah, I reached out to people in your campuses. So yeah, so Tifton and Griffin. I know Tifton for sure. Griffin, I'm still waiting to hear back. But I reached out to them as well to have someone print and proctor the exam as well. So that's
Okay.
Yeah, so again, it's
Awesome.
gonna be in person, right? You have to go to your campus, whichever one of the 3 that is. No one online is gonna be able to take the quiz online. We will not need a computer sorry, not the quiz, the midterm. Not gonna need a computer for that either.